Okay, hello everyone. Here is Alexander Kozachinskiy, and this is my joint work with Vladimir Podolsky. Here is a brief summary of our work. First, we establish new connections between two classical areas of complexity theory. One is circuit complexity, and the other is communication complexity. In fact, such connections are known for a long time. Maybe the most notable example are Karchmer-Wigderson games, and in a sense we generalize these games in our paper. And from it we obtain some improved construction of threshold circuits for some functions, and not only these improved constructions are interesting on their own, in our opinion, but it turns out that they have some motivation in cryptography. So let me start with presenting our applications about threshold circuits, and just we deal with threshold functions of the following type. So first of all, these functions are Boolean functions, and for integer k, which is at least 2, we consider the following Boolean functions. So if the fraction of input bits, if the fraction of ones in the input is greater than 1 over k, then the function should output 1. And if the fraction of ones in the input is smaller than 1 over k, then the function should output 0. So 1 over k here serves as a kind of a threshold. And throughout the talk, we assume for technical simplicity that the number of input bits is not divisible by k, so that, no input lies exactly on the threshold, and we don't have to think how we define our function there. A major example of such a threshold function is just a majority function, which is a function when you take a threshold to be 1 over 2, right? And here are our main applications. So first we show that the majority function on 2n plus 1 bits can be computed by explicit logarithmic depth circuit. And explicit here means that the circuit can be printed out in deterministically in polynomial in n time, and in fact the circuit consists only of majority free gates and variables. And here I'd like to stress that we do not use constant zeros and ones here, and this is actually important. So just a remark, so majority free gate, what it is? It's just a threshold function on 3 bits with a threshold of 1/2, right? So as all majority functions. And it's a kind of the most basic majority function, or the most basic threshold function with the threshold of 1/2. So, and what's with other thresholds, right? We show that for any fixed k greater than or equal to 3, the threshold function on kn plus 1 bits with a threshold of 1 over k. So, for technical simplicity, we assume that the number of input bits is divisible, is 1 modulo k. So we show that this function can be computed by explicit formula of polynomial size and depth, now log n squared. And now each gate in the circuit is a threshold function on k plus 1 bits with a threshold of 1 over k. So again, just a remark that this threshold function is just, it receives k plus 1 bits on input and outputs 1 if there are at least 2 ones. So again, it's kind of, roughly speaking, this is the simplest threshold function, the simplest interesting threshold function on 1 over k with a threshold of 1 over k. So what is the history behind these questions? First of all, let's consider majority function. So, and in fact, it is known for a long time that one can compute majority function with a logarithmic depth formula consisting only of majority free gates, and the following simple construction does it. And this construction is essentially due to Wayland. So we can just take a complete ternary tree of logarithmic depth. Then we can just place into each internal node of this tree a majority free gate, and then so there are some inputs to bottom gates, and we just assign variables randomly, independently, uniformly at random to these inputs, right? And with high probability, one can show that the resulting formula coincides with majority. So this construction is great. So it's simple. In fact, the constant bit for log n is quite moderate. And the only drawback here is that this is a randomized construction. This is not an explicit construction. So the question is, can we do something similar deterministically and efficiently? So as a partial answer to it, one might say that okay, we know that there exists an explicit logarithmic depth monotone formula for majority, which can be extracted from the AKS sorting network. But what's the point is that in this formula, one uses Fanning tool and OR gates. But let's suppose that someone asks, okay, so but can we randomize Welian construction by using majority-free gates, right? By using only these majority-free gates, and it turns out that this question is not just a question of pure curiosity. It has some application in multi-party secured computation. So it's some area of distributed computing where there are some parties wanting to perform some common task, but they do not trust each other. So this is kind of a sub area of cryptography, and it is impossible in this video to go into much more detail. So, but anyway, motivated by these applications in multi-party secure computations, so Cohen et al. What they did, they first show that if pseudo-random generators exist, then fair randomization of Welian's construction is possible. So fair, again, it means that we use only majority-free gates. This is not quite obvious because, this is not at all obvious because one can just say, okay, let's use the output of a pseudo-random generator in a Welian randomized construction. But in this way, you will just obtain a lot of majority-free formulas, and most of them will compute majority, but how would you pick one out of this many? So, and what Cohen et al. Also show that now this is in a conditional result, we can fairly randomize Welian construction, so there will be majority-free formula of logarithmic depth, but it will be like only approximate randomization in the sense that the resulting formula coincides with majority function not for all or not on all inputs, but only for inputs where the fraction of ones is bounded away from 1/2 by some small quantity, which actually goes tends to 0 as n goes to infinity. But again, this works not for all inputs. So our result is just we remove this drawback and we show that fair exact derandomization is possible. And what we found with thresholds, this question is not that well studied. So again, so it was known that we can compute this threshold function on kn plus 1 bits with threshold 1 over k by these gates, but the best construction was just linear depth exponential size, and this, so no one even knew how to do better non-explicitly. In particular, Welian's trick here doesn't work. Welian's construction. And so again, this question is motivated by multi-party secure computation, at least in case when k equals 3. And what Cohen et al. Again showed that something similar to what they showed for majority function. So they showed that there exists explicit logarithmic depth circuit with only these threshold k plus 1 over k gates. But again, this coincides only with not on all inputs, but only for inputs where the fraction of ones is bounded away from 1 over k by some small, again, quantity. Okay, so what we do now, our result is incomparable. Now, we construct a circuit which coincides with our target threshold function everywhere. It's explicit, it has polynomial size, but depth is only log n squared. Okay, so now how we do this? It turns out that these results can be extracted from a new connection between circuit and communication complexity. So, but before going into that, let me recall classical connection. What is the Karchmer-Wigderson game? So, on one hand, we have a classical complexity measure, namely circuit depth. So, for simplicity, we will consider only monotone functions and only monotone circuits. So, and the depth of a monotone function f is just the minimal depth of a monotone circuit, that is a circuit consisting only of one and two AND and OR gates. Uh, and it turns out that we can define a similar thing in completely different terms, in terms of some communication games. So in these communication games, we have two guys separated from each other. One guy gets some x on which f such that f of x is 0, and the other guy gets some y such that f of y is 1. And what's their goal? They want to find some coordinate where x is 0 and y is 1. So why this task is even solvable? Why such coordinate exists? Well, because otherwise x is greater than or equal to y in every coordinate, and then this would mean that f of x is greater than or equal to f of y, but this is not the case. So at least this task is doable, and turns out that the monotone depth of f is the minimal number of bits of communication needed to solve this task. So in a sense, so what it means that these two parties, these two communication parties, can agree prior to everything, prior to the moment when they receive x and y, on some algorithm for finding this I. And for a given algorithm, we are interested in the total number of bits of communication parties transmit in this algorithm, for a given x and y, and then worst case overall pairs of inputs. And so the best algorithm, the algorithm minimizing the total number of bits communicated, uh, it just defines the monotone depth of f, just exactly. Okay, so and this theorem is quite influential. So a lot of circuit depth and in fact also formula size lower bounds were obtained via it. Okay, so and what's uh, what's with our new connection? So in which direction we generalize these games? So we have Karchmer-Wigderson games, and there are two parties, and they communicate according to some rules. But then we just asked ourselves in one moment, what will be a natural generalization of Karchmer-Wigderson games to more than two parties? It's not immediate because you see, we want this generalization to work for Boolean functions, but in Karchmer-Wigderson games, so Boolean functions takes two values, zeros and one, and in these games, one party corresponds to zero, the other party corresponds to one. So how would one fit the third party here? But then we just looked at the Karchmer-Wigderson game for majority function. In this game, so the first party gets some vector with 2n plus 1 bits, in which there are at most n ones, so majority is 0. And the second party gets some vector where there are at least n plus 1 1, so the majority is 1. And their task is to find a coordinate where the first vector is 0 and the second vector is 1. But then you see we can equivalently look at this from the following viewpoint. So now assume that the second party just flips each of his input bits. And now both vectors will have at most n1s because there are two n plus 1 input bits in total, right? And how our task reformulates. So before that, we had to find some coordinate where y is 1. And now, since we've flipped y, we need to find a coordinate where y is 0 and x also 0. So we had to find a common 0 coordinate. And in this form, we can naturally generalize this game to more than two parties. So let's assume that there are k parties, each gets a kn plus 1 bit vector, and each vector has at most n ones. So in total, you have at most kn ones. So there will be a coordinate where all k vectors are 0. And let's consider a task of finding some such coordinate. And this is just one more remark that we can equivalently look at this problem that by saying that each party gets a vector on which our function that the threshold function that we have already seen on kn plus 1 bit vectors with a threshold of 1 over k is 0. So by having this remark, we can just say, well, okay, let's consider a similar game for any Boolean function. So this will be called QK communication game for Boolean function f. Let's suppose that there are k parties and each gets a vector from a preimage of 0. And the task is to find a common 0 coordinate. So the objection here is that this is not solvable for any function, right? But anyway, let's consider this only for functions for which this task is solvable. So these are functions where any k elements of a preimage of 0 have a common 0 coordinate. Let's just denote the set of such functions by qk. So on the other hand, one can characterize the set qk in terms of circuits, and this is kind of a first mile step to our connection, to our new connection between communication and circuits. So, namely, it turns out that the set qk is exactly the set of functions that can be lower bounded by this circuit that we have already seen, by circuits containing only threshold function on k plus 1 bits with threshold of 1 over k as gates. So no other gates can be used. So uh, to see, so let's to understand at least the parameters, understand it in one direction. So suppose, so in which direction? Suppose that there is a function that is lower bounded by such a circuit. Namely, what does it mean actually? It means that if my function is 0, then then the circuit is also 0. So it just means that the circuit is smaller than or equal to my function on every input, right? So why is then this the function is belongs to qk? Because you can take just any k elements on which the function is 0, and then the circuit is also 0 on these k vectors. So um, the output gate of a circuit is 0 on k vectors, and each vector, this means that for each vector there is at most one, or so there are k plus 1 gates which are fed to the output gate, and for each vector there is at most one out of these k plus 1 gates on which this vector is 1. So there will be a common there will be the same gate where again all k vectors are 0. So this means that we can descend by one in our circuit to a gate where, again, all k vectors are 0. And by doing this, we will finally reach a variable where all k vectors are 0. And this means that in the coordinate corresponding to this variable, all these k vectors are zeros. So this means that our function is from qk, but just by definition, because we start with any k elements of the preimage of 0. Okay, so what does it mean actually? It means that, okay, so we have a function from qk from which the qk communication game is solvable. And on the other hand, we know that these functions can be lower bounded by such circuit. So our main result is a quantified version. In a sense, it's a quantified version of this fact. So we kind of, if it's solvable, if the communication game is solvable, then how many bits of communication you need for that? And on the other hand, if you can lower bound by such a circuit, our function, then what is the depth, minimal depth of such a circuit? And it turns out that these two quantities are equal, at least up to the constant factor. So, so again, the first quantity is the communication game, is the communication complexity of QK communication game for F, where F is some function from QK, and the other quantity is the minimal depth of a threshold circuit, the minimal depth of a circuit with this threshold k plus 1 over k gates that lower bounds f. Okay, so let's again understand the easy direction of this theorem. The easy direction is that if there is a circuit of small depth lower bounding f, then the communication game can be solved in small number of bits of communication. So this is kind of a similar argument that we already seen. So if so there are k parties, each gets a zero of a function f, and since our circuit lower bounds f, then the output gate of a circuit is zero on all these k vectors. Again, this means that there is a gate which is fed to the output gate and on which all key parties are zero also, right? And we can find it in constant number of bits because again, so like we treat everywhere we treat k as a constant. So after by constant number of bits of communication, we can descend in our circuit by one, and then so after at most d such steps, we will reach a variable where all k parties are zero, and this will be a coordinate where all their input bits are zero, input vectors are zero. Okay, so and how one can get, so the hard direction is the other direction, but let me probably I will finish my talk by presenting how we the idea how we get our applications from this result. So the one, let's consider our application for majority. So we want to compute majority by explicit logarithmic depth majority free circuit. So how we do that? So on one hand, we know that there is an explicit monotone formula for majority of logarithmic depth. And by the theorem of Karchmer-Wigderson, it means that Karchmer-Wigderson game for majority can be solved in logarithmically many bits of communication. And as I mentioned in my motivation of our multi-Karchmer-Wigderson games, the Karchmer-Wigderson game for majority is the same as our Q2 game for majority. So this means that Q2 game for majority can be solved in logarithmically many bits. And this means that there exists a majority-free formula. So by our main theorem, this means by hard direction of our main theorem, this means that we can transform a protocol for Q2 communication game for majority into a logarithmic depth majority-free formula lower bounding the majority function. But you see, this is close, but not exactly what we wanted, because we want our formula to compute majority. But there is a simple observation that any majority-free formula that lower bounds majority on 2n plus 1 bits actually computes majority on 2n plus 1 bits. Okay, there are several ways to see it. For example, one can say that, actually majority, the set of its zeros is maximally Q2. So you cannot add to the set of zeros of the majority function no more vector so that it is again Q2. Then, any formula that lower bounds majority cannot be zero on some input where majority is 1. Okay, this is just a simple actually exercise. And there is a lot of steps here, and what we should care also is that these steps, that the explicitness is maintained on all the steps. Okay, this requires actually some technical considerations, but this is kind of it's doable. And what is also can be said here is that in fact we can present, at least present, this construction like directly. So we can just take the Eki sorting network and show how we directly transform it into a majority-free circuit. And I hope this will be presented in a separate video. But let's again now consider the case of other thresholds. So recall that we want to show that for any fixed k, which is at least 3, the function, our threshold function with a threshold of 1 over k on kn plus 1 bits can be computed by explicit log n squared depth circuit with these gates. Okay, how we do this? We again, we don't have something similar. So we want to apply our theorem in a hard direction. So first, we would like to solve the QK communication game for our function in log n squared bits. This is actually it's quite easy to do that, because our QK communication game for this function is just each of k parties gets a set of size at most n in the universe of size kn plus 1, and they want to find any element which doesn't which lies outside all these k sets. So how they can do this? They can perform a kind of a binary search. So you know that the total number of ones in these k sets is at most kn. This is the smaller than the number of the universe. Hence, if we split our universe into two parts, in any way you want, this means that in either of these two parts, the same thing holds, that the total number of ones is smaller than the size of the part, right? So we can decrease the size of our universe by 2 while maintaining this invariant. But we should decide which of the two parts uh, 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 which of the two parts satisfies this invariant, right? We know that one satisfies, but which one? This can be easily done in logarithmically many bits, because the parties just can send each other how many elements of these sets they have in the first part and in the second part. So there will be log n steps, and in each steps parties send each other log n bits. So in total there will be log n squared bits. Again, this means that now this is our main theorem. It means that there is a threshold k plus 1 over k circuit of depth log n squared, lower bounding our target threshold function. Again, this is not quite what we wanted, because we want our circuit actually to compute this function, but again, this can be obtained for free by similar argument as for majority. Again, I'm not talking about here about the size issues. Again, explicitness is it also we should also be careful with explicitness, but this is all doable. Again, so the main open question here is to solve now this problem in less number of bits, namely, for example, in logarithmic n bits, so that we will obtain the similar formula, but of depth log n. Okay, so this is the main open question that is left, and let me thank you for watching.